Okay, so let's have a quick look at this is nothing new. This is exactly the stuff that we've been going through with a different parent graph. That's it. Okay, so this time our parent graph is going to be f of x equals x squared, right? So let's take just a brief look. What does that graph look like? So if I'm just graphing the function, the parent function, f of x equals x squared, what do you know? Brent, close it up real quick. So it's a parabola, isn't it? Yeah. Okay, it's a parabola. So what are some key points? What's the most important point on the parabola problem?
0, 0.
0, 0. What do we call that?
The origins.
That's the origin. You're right. You're right. But what do we call that point on a parabola? It's kind of the... It's a special point. You're right. It's our special point. Vertex. Yeah, that's what we call a vertex. So there's the vertex. What's another point on this function? And I want you guys to get used to, I haven't kind of leaned on this idea much in the past, but because I've wanted you to really focus on transformations. But thinking practically, if you're on a test, for example, and you want to know which graph is, which function is which graph, just think about this kind of just really pragmatically. How could you get the answer quickly? All you ever really have to do is make a t-table, right? I mean, we just have to get some points. Like we know right here, if we're going to plug in values for x and find out what the y values are, yeah, we'd have one of them is going to be at 0, 0. One of them is going to be at 1, 1, isn't it? If I plug 1 in, f of 1 is just 1 squared, which is 1. What about negative 1? What's negative 1 squared? 1, yeah. What's 2 squared?
1.
4. Yeah, right. 2 times 2 is 4. And then negative 2 squared is also 4, isn't it? Right?
Yeah.
So what's the picture we get? Well, okay, so when we go over 1, we go up 1. When I go over 2, I go up 4. If I go over 3, I go up 9, etc., right? If I go back 1, I go up 1. If I go back 2, I go up 4. And so look what we get. We get a function that has this kind of symmetry, doesn't it? It has folding symmetry. We'll talk more about symmetry in the future. But for now, we can see that clearly if I fold this thing over the y-axis, it lines up, doesn't it? Okay? So we'd say, one other thing we can say, and this isn't going to be a huge deal to us now, but we'll come back to this. It'll be a bigger deal later. We could say that that line right there is what we call the axis of symmetry. Okay, why is that the axis of symmetry? Somebody explain to us. Why would we call it that? Because it's symmetrical. Yeah, that's like the crease in the paper if we fold this thing on itself, right? Okay? So that's our parent graph. No big deal. We've dealt with harder ones than this, actually. A square root function is probably harder to deal with than this one is, right? We did absolute value graphs, which I think are about equal to this one in terms of complexity, and square roots are even harder. So these kinds of problems are no big deal. You guys can already do these. It's some additional practice, but I kind of want you to get used to dealing with parabolas, because we're going to talk about parabolas for the next, between now and Christmas. We're going to just really hit quadratic stuff pretty hard, starting with graphs, and then we'll get into solving quadratic equations, and it'll all kind of come together though. So what do we do here? If we're going to start with our parent graph, f of x equals x squared, and we want to produce a transformation of that, some new graph g of x that does this stuff, well, let's just add that stuff one piece at a time, because we want to do this in order. So what does this mean right here? If we're going to vertically compress f of x by a factor of 4, what is that? Which parameter does that? What are our 4 parameters? Let's review. It's been a while. Yeah, we had a long break there. What were the 4 parameters that we always introduced, the 4 special numbers that we use to tweak absolute value graphs and square root graphs in the past?
I have no idea.
So let's write this down. Okay, So let's just we'll write down what g of x is in terms of f of x. Okay, so what's the parameter that, say it again?
A, B, H, and
A, B, H, and K.
A lot
Good.
of numbers.
Right, right. Those are our special numbers. We call the fancy word we use in math is a parameter. Why is it a parameter? Okay, because a parameter is something, it's like one of the dials. When we dial in a line, the parameters are M and B, right? They're numbers that are going to be specific to one graph, but they could vary from graph to graph, right?
M and X.
So like M and B, if we're dialing in a line, for a given line, we would have a certain slope and a certain y-intercept, right? Are those constants or variables? Well, they're constants for that line, aren't they? For that one line, they're never going to change. X and y are variables, right? Those are always variables. If I choose a certain x value, even on that one line, as an ant walks along the line, he's going to change his x and y coordinates. But the slope would always be the same for that line, and so would the y-intercept, right? But if I want to draw a different line, I'd have to change those numbers. So they vary from, from shape to shape, from line to line, or from parabola to parabola, or whatever we're dealing with. But once you're talking about a certain function, they're dialed in and they stay there. They're constants for that function, right? So that's what a parameter is. It's kind of halfway in between a variable and a constant, if you want to think of it that way. So one of them was A. Where does that one go? Where does A go? If we're going to write g of x.
We're right behind the F.
Right behind the F?
Yeah, that's where the A would go.
Are you sure?
F.
You're thinking of B, I think. A goes in front of everything, right? A's out in front of everything, in front of the function. That's what we're multiplying the function by, okay? Now what about B? Where's B go?
In front of the X.
Okay, good. So B's going to go here, right? B goes in front of the x minus what?
H.
H. Aha. Okay, so there's where my H goes.
Plus K.
And then outside of the whole thing, at the end, we've got our plus K. And think what these did. A was responsible, we associate that with vertical dilations and reflections. B we associate with horizontal dilations and reflections. H is
Up and down. Up, side to side.
side to side, horizontal translation. K is
Up and down.
vertical translation. Good. And so for us then, okay, so if we're going to do all this stuff, right? So if we're going to vertically compress by a factor of 4, so that's going to be associated with which parameter? Vertically compress.
A.
Oh, hang on. You know what? I don't like something about this. I really don't like something about this. You know what I did? Okay, I need to change these a little bit. That shouldn't say compress, should it? Compress doesn't fit. I got to tweak these just a little bit.
Stretched.
Yeah, it's not going to be stretched because if it's a factor of 4, if we're multiplying by 4, that's not a compression, is it? Right? That's going to make it bigger. So this question is kind of messed up, and I'll fix it. I'll go through and look at all these and fix them. That's going to be a stretch, isn't it? We're going to vertically stretch by a factor of 4. Okay. So that's a value of A, isn't it? Right? So that's telling us right away that A, the red part is telling us A equals 4. So 4 is what goes there, right? Okay. So step 1. Step 1, we know that g of x equals 4 times my parent function, which is x squared. Okay, there's step 1. Step 2, new color. Now we're going to vertically reflect f of x. So what's that going to do?
-1 where the B's at.
Now we're vertically reflected. So we're going to reflect this way. That's a vertical thing, right? That's not, B is horizontal stuff.
Oh, so
right?
it's got to be a negative?
Okay, so A is going to be negative, isn't it? Okay, so all that's going to do is that's just going to make that 4 negative, right? So far, so good? Okay, we're going to translate, new color, we're going to translate f of x 3 units down. So what's that going to do?
Move it down 3.
Okay, so down 3, where does that go?
Okay.
Okay, so that goes outside of everything. I'm just going to subtract 3, right? And then finally, if I want to translate 6 units to the right, what's that one gonna be? If I'm gonna go 6 units to the right, that's telling me,
You gotta go left. It's plus 6.
okay, so h is 6, so I'm gonna subtract 6. That's telling me that h is equal to 6, so I'm plugging in a 6 right there, aren't I? Right? Let's see, the orange one, let's not forget that. That was, we're plugging in a -3 for k, right? So I'd almost have to kind of rewrite this thing, wouldn't I? Because I've got to replace the x with the quantity x minus h. And so this is going to end up looking like g of x equals -4 times the quantity x minus 6
Minus
squared minus 3, right? Okay, everybody good with that? That's my answer, right? Okay, how about something like this? So we want to write a function of this form that represents this graph. So what's all the stuff that's been done here? Let's compare this to the parent graph. Okay, what have we done? So if here's my parent graph, starts off here, and it's going to go through that point, over 2, up 4, over 3, up 9, right? And then same thing on this side. What have we done here? Okay, so what number could we plug in for h and k? What numbers?
3 and 1. 1 and
So here's my special point, right? The special point is always going to be the point that starts off at the origin. Where does the special point end up?
To left 3 up.
Left, I think left 2, up 1, right? So would everybody agree then, if we do that, if I go left by 2 and up by 1, well, another way of saying that is, what are the coordinates of this point?
-2.
Yeah, -2, 1. And what did we say last unit? We talked about, for a parent graph, the special point that starts at the origin, when we transform it, that special point is always going to have coordinates h and k, isn't it? Right? So this is just telling us that h is -2 and k is 1. Well, that helps, right? So we can plug numbers in. -2 goes in for h, +1 goes in for k. Now what about b? What can we say about b? Right? What's our horizontal dilation factor going to be here? So how much is this, what are we multiplying by horizontally? Well, normally, it looks like, let's compare these 2 points, this point and this point, right? That's going to be our starting point, right? Normally, we would go up by 1 and over by 1, right? That's what we did here, right? Normally, up 1 and over 1 would be normal, right? For a vertical distance of 1, our horizontal distance would be +1. Okay, what's going on here though with this one? Now for a vertical distance of 1, we're going to the right by 3, right? You see what I'm saying? So what's that telling us about our b? For a vertical distance of 1, instead of going to the right by 1, we're going to the right by 3. So what are we multiplying our horizontal distances by? 3. Everybody agree? We've stretched it out horizontally by a factor of 3. This point right here has been stretched over by 3. It turns out it's also been reflected, but we'll get to that in a second, right? Everybody see that though? Okay, so our horizontal dilation factor, another way to think about it is, we're going to write it in terms of, we always do final value divided by starting value, right? So what's the final value? So the final horizontal distance, we'll just call that delta x, x difference, right? Divided by the starting or the initial horizontal distance. What are those numbers? What's our final horizontal distance?
3 and 1.
It's going to be 3, isn't it? Good. Positive 3. What's our starting horizontal distance? 1. Good. So the horizontal dilation factor is 3. Okay, so we're multiplying by 3 horizontally. B's tricky though. What's B going to be then? It's reciprocal, isn't it? So whenever we're multiplying by horizontally, B is going to be the reciprocal of that, right? So we're plugging in a 1/3 for B. But there's one other thing that's happened here too. We've also flipped this thing vertically. So how do we do that?
And negative in front of the A.
Yeah, so negative A is -1, isn't it, right? Because this thing has been flipped, we also have to add in here A equals -1, which means we're just going to put a negative out in front, the whole thing, right? In front of the function. So our answer then, what would it look like? So we'd end up with our function, our blue function here is going to be -1/3 times x minus -2. What's that going to look like? Plus 2. That makes sense, because remember, when we do x plus 2, we're going left 2, and then outside of everything, we're going to add 1. So that's our answer right there, isn't it? Okay.
Square. What is it?
Oh, I forgot the square, didn't I? Yep. Yeah, where does the square go?
And parentheses?
Yeah, behind the bracket, right? Right
Oh,
there.
okay.
Because all this stuff is in the function. Okay. Remember, the h and b always go inside the function. A and k go outside the function. Okay. Last one. Call it good for today. So what if we were going to graph this thing? For now, this is fun. What would that look like?
Upside down like the other one, because the A is.
Okay, good, good, yeah, good. We see some stuff here, don't we? We see that A is -1. Okay. What's the value of B?
A 3.
B equals 3, right there, isn't it? Okay. So what's our horizontal dilation factor going to be?
1/3.
1/3. So is
Is
that
that
going to be?
1/3 or just 1/3?
Say it again.
Is it negative 1/3 or just 1/3?
Just 1/3. Just 1/3 because B is 3, right? So if B is 3, it's just going to be the reciprocal of that.
Oh, yeah.
What's H?
2 plus 2.
Yeah. Well, hold it. H is it's a little tricky.
It's -2.
-2, isn't it? It's -2 because that's the number that's being subtracted from x. Okay, and then let's see what else we got here. How about,
K.
yeah, what's K?
-1.
Okay, and that goes right there. Okay, there's one other really tricky thing here. What about that?
-1.
What happens when we multiply just the x by -1? What does that do? Remember?
Flip it over.
Flips it over what?
Isn't it the Y?
Flips it over the y-axis, yeah, right? So that little, I mean, that doesn't seem like much there, does it? That's a bad color. Pick a different color here. Oops. Let's get it's orange. Okay, so this one right here, what's that going to do? That's going to reflect over the y-axis, right? So we got to do all that stuff to it then, right? All that stuff to it. So what's this thing going to look like? It's a lot of stuff to do. This is a pretty complex problem, really. So what are h and k? -2, -1, right? So we know that this thing's got to go back 2, down 1. That's going to be our vertex. Okay, what else here? We know that B is 3, so it's being compressed horizontally by a factor of 3, right? So let's pick a convenient point. Now, normally, we'll draw just a parent graph here. Normally, if I went over by 3, how far up would I go with a parabola? 9. Okay, so that means I've got to go clear up to 1, 2, 3, 4, 5, 6, 7, 8. 8. Clear up there, right? So I'm going over 3, and I'm going up 9. But if I'm going to be multiplying by 1/3, my horizontal distances. Instead of going over 3, how far am I gonna go over?
1,
1.
up 3.
Yeah, good. So we're gonna end up with, ours is gonna be over 1 and then still up 9, because I'm gonna squeeze that point in, right? So there's my axis of symmetry. It's gonna be a really tall, skinny parabola, right? It's gonna look like this. Right, so far. What does this negative out front do? You're gonna flip it vertically, good. So that takes us up to something that looks like this, right? So it's gonna be a tall, skinny parabola that's down. And then last thing, now we've got this reflect over the y-axis. Because I've gotta do the whole thing, and then the last thing I do, I've got this negative x in there, right? Which means everything that we would have normally done up here, right? That would be our answer. This bottom parabola would be our answer if that was it. But now, when we multiply the x by -1, it takes that whole thing and reflects it over the y-axis. And so our answer is actually gonna look like this. Instead of being backwards 2, we're gonna have to go over this way 2. So there's where the vertex ends up being, right? So we've got this tall, skinny parabola that's right there. Okay, does that make sense? It's a lot of stuff to put into one problem. If you, I mean, that's pretty big time. If you can do that, if you can get problems like that, you're doing a pretty good job. Okay, I'm done for today. That's a lot. Have at it.